Learning Target 2F in this video. In the first part of Learning Target 2F, we learned how to graph linear inequalities in two variables. And in this video, we're going to focus on how I can graph absolute value inequalities in two variables. So we're going to use a lot of the skills that we had in the first part of this video, whether that's determining how we shade and testing a point, as well as if our boundary line will be solid or dotted. The difference with all of these graphs, though, is each one of these inequalities has an absolute value in them, which is going to change the shape of our graph. Before, we were looking at linear inequalities, so all of our graphs are straight lines. In this video, we're going to look at graphs that have absolute values in our inequality, so all of our graphs will be a V-shaped graph. And to help us graph those, we're going to rely on our prior learning target, where we learned about the transformations and how to apply those transformations to our start point of the parent function to see what our final points would be that we're going to graph. So looking at example 5, we have y is greater than 3 times the absolute value of x plus 1. The first thing we need to do is figure out what our transformations are so that we can apply those to our start points. Why don't you guys pause the video right now and list your transformations for this equation in example 5. So in example 5, we have two transformations. The first transformation is coming from that 3 that is being multiplied to the absolute value of x. And since that 3 is bigger than 1, we have a vertical stretch by 3. The second transformation is coming from that plus 1 that is being added to that absolute value term, and that is our vertical shifts. And since we're adding 1, that is going up 1. Now we have to remind ourselves, well, what does this do on a coordinate level? Well, any vertical stretch or compress is changing the y-coordinate, and we are multiplying that y-coordinate by our stretch or compress factor. So in this case, we're going to multiply, y, let's add the variable in there that we're after, so we're multiplying y by 3. For our vertical shifts of going up or down, that's also changing the y component, and if we're shifting up, we are adding that number, so in this case I'm going to add 1 to all the y values as well. And because both of these transformations are affecting the y-coordinate, that's why it's so important that we're applying the transformations in order. So the stretch by 3 has to come before the up 1, otherwise we wouldn't end up with the correct graph. Now our start points for an absolute value come from the parent function. That's that -1, 1, 0, 0, and positive 1, 1. And we're going to apply the transformations to these. So the first transformation I'm going to apply is that stretch by 3. So I'm multiplying the y components by 3. The x components stay the same, so I can go ahead and rewrite all the x values. Now when I multiply all the y components by 3, 1 times 3 gives us 3. 0 times 3 is still 0, so that coordinate pair didn't change. And then 1 times 3 is 3 again. Now our second transformation to apply is that up 1. So again, the x coordinates are staying the same, so we can go ahead and rewrite all of those x spots. And when we add 1 to y, 3 goes to 4, 0 goes to 1, and 3 goes to 4 again. Now that we've applied both the transformations, which are all of our transformations, these are the final points that remember that we are going to graph. So let's plot these on our graph here. So we have -1, 4, 0, 1, and 1, positive 4. Now before I start connecting these together, I see that they're going to form a V shape that is facing upright, which is correct. It looks like they've been stretched since our distance between the vertex and our other 2 points are now further apart, as well as that graph has been shifted up 1 from the vertex I can see. Now before I connect these together, I have to decide, will I be connecting them with a solid line or a dotted line? What do you guys think? So in this case, I'm going to be connecting them with a dotted line because I have that greater than, just strictly greater than inequality. And because there is no equals to bar, that got a little messy, and I just have a strictly greater than, this will be connected by a dotted line. So I'm going to go ahead and dash or dot my dotted line on here. And it's still creating that V shape. So the shape of the graph hasn't changed. I'm still getting a V. The boundary line here, though, instead of being solid, is dotted. Now the last thing we're left to do in examples like these is I have to figure out where my entire solution set is. since this is an inequality, it involves shading. So I don't just have one answer. I don't just have my boundary line here that I'm graphing, but I have all the points, all the coordinate pairs that make this equation true, and that's representing in our shading on our graph. So to determine our shading, we need to test a point just like we did before. So I'm going to go ahead and test 0, 0, and I'm allowed to do that because 0, 0 is not on my boundary line. So if I put that red X again at 0, 0, I can see that that's not on my boundary line, so I'm good to test it. And I don't have to test 0, 0, I can test any point, remember, that's not on our boundary line. I'm just choosing 0, 0 since it's an easier point to test. And I'm subbing it into the original inequality and asking myself, is 0 bigger than 3 times the absolute value of 0 plus 1? So I subbed in 0 for x and 0 for y. Well, let's simplify this down. I still have 0 greater than, and then on the right side, the absolute value of 0 is 0. 3 times 0 is 0. And if I add 1 to that, I end up with 0 bigger than 1. Now, is 0 bigger than 1? Is that a true or a false statement? So that is going to be a false statement. 0 is not bigger than 1. 1 would be bigger than 0. And so in this case, when the statement is false, remember we shade in the opposite area as our test point. So I'm going to shade opposite 0, 0. Since 0, 0 is outside this function, so I kind of have, instead of a straight line now, I have this V shape. So when I look at the graph, I have two options. I'm either inside the V, which I like to think about as on the pizza slice, or I'm on the rest of the coordinate plane, which would be the whole rest of the pizza there. Since 0, 0 is on the majority part of the pizza here, and I want to shade opposite 0, 0, my shading is going to happen inside the pizza slice then, since I want to shade where 0, 0 is not. And so this whole area in here, that whole pizza slice then is going to get shaded. So our answers here are going to look a little bit funnier than they did in our last video because I don't just have straight lines now. I have these absolute value graphs, and so I have either inside the pizza slice or I have on the whole rest of the pizza. And since 0, 0 came out to be false for this inequality, I don't want to shade where 0, 0 is. I want to shade opposite 0, 0. And since 0, 0 was on the entire pizza, I want to shade on the slice instead. Okay, let's look at our second example. So in this example, we have y is less than or equal to the absolute value of x plus 2 minus 3. First thing we want to do again is list our transformations. So why don't you guys pause the video right now and list our transformations for example number 6. So in this example, we have two transformations again. The first transformation is coming from that plus 2 that is inside the absolute values. That's going to be a horizontal shift. And since it's x plus 2, this is telling me that we are going to the left 2. My second transformation is coming from the negative 3. Since I'm subtracting from the absolute value, that's a vertical shift because it's outside the function. Because we're subtracting, this is going down 3 this time. Now we have to think about how this affects our coordinates. So if I go left or right, so those horizontal shifts, that's affecting the x. And since we're going to the left 2, I'm going to be subtracting 2 from all of those x values. And when we go up or down, that's a vertical shift, and that's affecting our y variables. And since we're going down 3 this time, I'll be subtracting 3 from all of our y values. So I have that left 2, which is subtracting 2 from all the x coordinates, our down 3, which is subtracting 3 from all of the y coordinates. I still have the same start points because my original parent function here is the absolute value of x. So I have negative 1, 1, 0, 0, and 1, 1 to start. Those are true anytime our parent function is the absolute value of x. And now we're going to apply the transformations. So my first transformation that I'm applying is that left 2. So I'm going to subtract 2 off from all of the x's. So negative 1 minus 2 will leave us at negative 3. 0 minus 2 will leave us at negative 2. And 1 minus 2 will leave us at negative 1. Now the y's stay the same, since I was only changing the x coordinates by going left 2. Now we're going to apply the second transformation. So the x coordinates stay the same this time, so I can rewrite all of those. But the y components I'm going to subtract 3 from. 1 minus 3 will leave us at negative 2. 0 minus 3 will leave us at negative 3. Then 1 minus 3 again will leave us at negative 2. These again are our final points here, and these are what we're going to end up graphing. We're graphing these points since we started with our start points that come from the parent function of y equals the absolute value of x, and we applied the two transformations from there. So let's plot these. We're at negative 3, negative 2, negative 2, negative 3, and negative 1, negative 2. I always want to kind of double check and make sure that this makes sense. So my original graph was a V with a vertex at the origin, and then that graph went left 2 and down 3. So my vertex here should be at negative 2 comma negative 3 then, because I just went left and down. There was no stretch, no reflection, no compression here. Now when we go to graph this, it will create a nice V facing upright. And will that line be solid or will that line be dotted? So in this case, I'm going to have a solid boundary line since we have that equals to bar in our inequality. So since we have that less than or equals to, it's going to be a solid line. So I'm going to go ahead and insert a nice solid line for us going through. Oops. There we go. And I want to make sure I'm extending that all the way. I can make it a little bit bolder. Now we also have our second branch here that we need to insert in. Starts at the vertex and goes to the left side. And again, I want to make sure I'm extending this all the way because I want to be able to see my final shading. Oops, let's make sure it goes through the coordinate pair there. And I want to see my final shading, so I want to make sure my graph is extending over the entire coordinate plane here. Now what's left to figure out is where this graph will be shaded. I'm not done yet, and I know that I need to shade because I have an inequality here. And in inequality, I don't just have that one solution on my graph, I have that whole solution set, which we represent by shading. So we need to go ahead and test a point. I can test any point that's not on my boundary line, and in this case, if I put that red X at 0, 0, that will work out. So I can go ahead and test 0, 0, since 0, 0 is not on my boundary line. And when I'm testing 0, 0, or when I'm testing any point that's not on my boundary line, we're subbing that into the original equation, and we're trying to determine if that would give us a true or a false statement. So when I sub this in, I get is 0 less than or equal to the absolute value of 0 plus 2, minus 3 outside the absolute value bars. Well, let's simplify it down and see what happens. So I still get 0 less than or equal to. 0 plus 2 is going to give me a positive 2. The absolute value of 2 is 2, so I end up with 2 minus 3. So I end up getting is 0 less than or equal to, well, 2 minus 3 gives me a negative 1. So is that a true or a false statement? So in this case, 0 is not less than or equal to negative 1. That is also a false statement again. And so since I have a false statement, I want to shade opposite where the test point is. So when I look at this graph that I have here, I have my pizza slice, which would be everything like inside those absolute values, and that's where 0, 0 is falling this time. And then I have the rest of the pizza, which is everything outside. Since my test point came out to be false, I don't want to shade where 0, 0 is. Instead, I want to shade opposite that, and I'm going to shade on this whole rest of the pizza slice this time. So all of this region gets shaded as I get I get actually up to that boundary line, and the whole rest of the pizza there gets shaded around. And that would be our final answer then. I have the whole outside portion of this shaded. Since the test point came out to be false, I have to be on the opposite side as that test point. So we've seen two examples where we applied our transformations to figure out what our graph of our absolute value would look like. Since these are inequalities, we have to worry about, is the boundary line going to be solid or dotted? Then we also have to figure out our shading. And we've incorporated a lot of things in these last couple units, or in these last couple learning targets, so let's kind of recap what we have here. And we've got to really be able to answer these questions. It's not just about solving specific problems, but it's about thinking about what's happening in the overall picture here. So I've got 3 follow-up questions for you guys. The first one is, how can we tell if the boundary line will be solid or dotted? The second one is, how can we tell when we should shade or not? And how can we tell if our graph will be a straight line or a V-shaped graph? I want you guys to pause the video right now and answer those 3 questions and think about generally over the last 2 or 3 sections, how were we able to determine this? How was the boundary line solid versus dotted? When were we shading? When were we not? And how could we tell if our graph of our boundary line was going to be a straight line or a V-shaped graph? Okay, let's check those answers. So we have here is our boundary line will be dotted if I have that less than or greater than inequality. That will produce a dotted boundary line. If I have a less than or equal to, a greater than or equal to, or just an equals to bar, that boundary line will be solid. To determine the shading, if I have an inequality symbol, so if I have a less than, a greater than, less than or equal to, or a greater than or equal to, my graph has to have shading on it because it's an inequality, versus if I just have an equals to sign and I have an equation there instead of an inequality, I would not have any shading because I just want the exact value where they're equal to, versus with an inequality, I need that entire solution set. And for our last question, how can we determine if the graph will be a straight line or a V-shaped graph? Well, it depends on what type of function we have. If we have a linear function, so something like y equals mx plus b, where there's no absolute value bars in here, then my graph is going to be a straight line. If I have absolute value functions, like y equals maybe a times the absolute value of x minus h plus k, that's an absolute value function, and we know that the parent function for that is a V-shaped graph, so any transformations of that graph will also be a V-shaped graph. It's important to think about the overall picture here because we've looked at a lot in the last couple sections, and it can get really confusing to figure out, well, what am I supposed to do in this problem? Because all of the instructions are the same. It says graph our answer. We have to figure out what that solution set is. It doesn't tell us to shade or not to shade. That's implied in the question, and it doesn't tell us what type of graph we're going to get. That's also implied in what type of function is given. And we have to be able to identify how we know when this boundary line is dotted or solid, how we know if we will have shading on our graph or not, and how we'll know if we have a straight line or a V-shaped graph. So it's important to think about on a general level what's happening here so we can figure that out. Now, using this information, we've got 6 more examples here, and we're not going to actually solve them. So without solving, we just want to determine if the graph would have shading or no shading, if the boundary line would be solid or dotted, and if the graph would be a straight line or a V-shaped graph. So what I want you guys to do right now is, using this information that we talked about up above, answer questions 7 through 12 and determine for each one of these, would the graph have shading or no shading? Would the boundary line be solid or dotted? And would the graph be a straight line or a V-shaped graph? Okay, let's check those answers. So, on problem 7, we had y equals the absolute value of x minus 1 plus 7. In this case, there is no shading, and the reason there's no shading is I have an equals to sign here, not an inequality. Because of that equals to sign, that's the other reason why that boundary line will be solid. And I have a V-shaped graph here because I have those absolute value bars in my equation. Looking at example 8, we have y is less than 3 times the absolute value of x plus 1 minus 4. In this case, there is going to be shading because we have an inequality sign here. I have a less than. Also, because I have a less than, my boundary line will be dotted. And again, we have a V-shaped graph here because of those absolute value bars in this inequality. Looking at example 9, we have y is greater than or equal to negative 2/3 times x plus 9. There's shading for this guy because of that inequality sign. That inequality sign does have the equals to bar, so it will be a solid boundary line. And in this case, we have a straight line here because we're of that form, y equals mx plus b. Or not equals, we do have that inequality, so y is greater than or equal to mx plus b. But I have no absolute value bars in this equation, so this would represent a straight line when I were to graph it, where I could find my slope, which is negative 2/3, as well as my y-intercept, which would be 0,9, and we could graph it from there. Looking at example 10, we have y plus 2 equals the absolute value of x plus 3. So in this case, there is no shading since I have an equals to sign instead of an inequality. That's also why I have a solid boundary line. And in this case, although y is not isolated, I could subtract the 2 over, Move the 2 to the other side and have y equals the absolute value of x plus 3 minus 2, and that is producing that V-shaped graph for us there because we have those absolute value bars. In example 11, we have 2 times y plus 10 is less than x. So in this case, we do have shading since we have that inequality sign. That inequality sign doesn't have an equals to bar, so we will have a dotted boundary line. And in this case, we're back to having a straight line again, because although y is not isolated, I could take this equation of 2y plus 10 is less than x, and I could solve for y. I would subtract the 10 over first, have 2y is less than x minus 10, and then from here I could divide everything through by 2, and in that case, because I'm dividing through by a positive number, the inequality sign will not flip, and I'll end up with 1/2 times x minus 5, since I have to divide each piece through. Here I can see that this is of the form y is less than mx plus b, so I have my slope of 1/2, my y-intercept of 0, -5, and this is a linear function. Again, there's no absolute value bars, and that's why I'm getting that straight line as my graph. Now in our last example, we have y is less than or equal to negative absolute value of x plus 1 minus 5. In this case, we are shading again since we have that inequality sign. That inequality sign has an equals to bar on it, so my boundary line will be solid. And in this case, we have absolute values, so we are getting a V-shaped graph. And with all of these graphs that are absolute values and produce that V-shaped graph, we would graph it by identifying all of our transformations. So in example 7, I went right 1 and up 7. In example 8, we went left 1, stretched by 3, and down 4. In example 10, once we move that 2 over, we can see that we went left 3 and down 2. And then in example 12, we went left 1, reflection over the x-axis, and then we went down 5. So when we have those absolute values and we're getting that V-shaped graph, we're applying our transformations after we identify them, versus when we're getting these straight lines like in examples 9 and 11, we're wanting to isolate y so that it's in slope-intercept form, identifying our slope and our y-intercept and graphing from there, just like we did in prior sections. So this is the end of learning target 2F. We're going to continue to practice this in class.